So we're finally cracking into Chapter 8, vibration. This is the hardest chapter of the course. The coverage here says we cover force vibration, but we don't. Vibration without any external excitation is hard enough. You throw another thing in there, the average is going to be -%. We will focus or spend a little bit more time on recap, just because the physics behind it is actually pretty important. You have to understand the problem. So we start with a pretty generic mass spring system. So when it's horizontally sitting, this is basically, has a delta X of 0. Basically means the spring isn't deformed, it isn't stretched, it isn't compressed. Usually we assume there's no friction. If there is friction, then it's going to basically kind of break the vibration. Or not breaks it, but it dampens it. Now, when a system is sitting there, nothing's happening. It's not very exciting. It happens when we mess with it. So in this case, let's push it to the right by delta X. Now, remember your spring force, Fs. They're like your rebellious teenagers. If you tell them to go right, they go left. This is why there's a negative sign. Very important. So you put a block right, the force is going to pull itself to the left. If you push it to the left, you're compressing a spring, then the force is going to be in the opposite direction, always a negative sign. In this case, the weight and the normal distribution, or the normal reaction, does not do anything. And the idea is that because you stretched it, so Newton's second law, F equals ma in the x direction, it's going to accelerate the block back to the left. When it reaches the equilibrium, that spring force becomes 0, but because you're accelerating the block, there's a momentum. So just because the spring force becomes 0 doesn't mean it stops. The momentum carries it. So then, the spring has to overcompensate and push it back out, so it turns into this kind of tick-tock back and forth motion. The other configuration is hanging it off. The physics actually doesn't change. The only thing that's changed is the equilibrium position. Delta X as times 0 does not equal to 0. In fact, because the spring has to support the mass of, or the weight or the mass that's hanging at the bottom, it's going to basically originally be stretched. And you have to account for that. But if you're just looking at the response, the weight actually doesn't matter. So the Fs is basically at equilibrium is equal to the weight. If you mess with it more by pushing it down more, it's just going to be the weight plus k times y. This is not Newton's second law. This is just basically expressing the spring force. And if you apply Newton's second law, the W term actually cancels out. The only reason why in assignment 9, question 2, it was you have to consider it is that so you started with basically one mass, but then you basically mess with it by putting additional mass. So your weight changed. So in that case, you do have to account for it. Questions so far? Okay. So some animations, so pendulum. So technically there's a spring, or sorry, a tension in the rope, but basically it's just a swing back and forth. Your gravity, your gravitational force is what doing, or the only force that really matters on a system. And if you break it into nt coordinates, the n one isn't quite interesting. It just points out where the tangential component actually becomes a unsteady or like periodic force where it flips direction. It's actually what's keeping your pendulum swinging back and forth. And so that actually is what's sustaining the system. In real life, this would eventually slow down, so because of air resistance, but the animations will run on until my battery dies. Now, how does that relate to what we're learning? So when you look at mass spring system, so it's missing a horizontal line here. It's basically just a floor. The green line represents your spring, spring force, and then this shows you a direction. Now, the idea is that when you release it with a little bit of an initial displacement, it's going to swing back and forth. So it actually behaves very similarly compared to basically your tangential acceleration in a pendulum. And if you, let's say, increase the initial displacement, it's not going to change much besides the actual amplitude. It's not going to change the omega n, the natural frequency, which is depending on your spring stiffness and your mass. The only way to actually affect the natural frequency is by basically changing your K. So let's say we go from 10 Newton per meter to 50. So your natural frequency is going to be higher, but remember this is square root K divided by M. So just because your spring stiffness is 5 times higher doesn't mean your natural frequency is 5 times higher. It's square root of 5, roughly 2.25 in this case, which checks out. Questions? So I made chocolate. Okay. Yeah. Anyone came in late, so it's like a last class tradition, 2 chocolate each. So also you, yeah. Just leave it back here. If there's any leftovers, I'll grab it at the end. There's also a class plaque that passed around to sign. Questions about simple harmonic motion, SHM, so far? Okay. Right. Case A, where we're basically just going horizontally. This is basically chapter 3 stuff. You apply Newton's second law, F equals ma. Now, when it comes to chapter A vibration, the people who came up with this has a bit of an OCD. We don't like using Vx or Ax. We like using x dot or x dot dot. They mean the same thing. It just means the second time derivative, d squared dt squared. So you do that twice for x, you get horizontal displacement or acceleration. The reason is that sometimes we also have like a y direction, and then later on when you do rigid body, you also have theta. So this is a little bit quote unquote cleaner. So if there's no friction, most of the time you won't have one, then you just get negative spring force equals ma. We should clean it up by throwing everything to one side. And again, we are pretty OCD about this chapter. We don't like anything in front of our x dot dot, so we divide the entire equation with m, which is basically where omega n squared comes from, square root of k divided by m. Questions? Okay. This is known as a standard form. Again, nothing in front of our x dot dot. This basically tells us kind of like the motion of the equation or the system, but it's not quite convenient. But let's talk about the vertical one. So we do have to account for basically the additional sagging because of your mass, which is basically a delta st, static deflection. They don't usually play a role. It gets canceled out unless your system has changed halfway through the problem. Otherwise, it's basically just k times your y. The other term will get canceled out. Questions? Okay. So again, as the mass that you're heading off gets heavier, it sags more. Pretty straightforward. Now, the way in terms of the way they behave in terms of like horizontal or vertical doesn't actually change much. So the only thing that changes is so you basically hang off a little bit with a delta st. But let's say you started like further down, so you dragged it a little bit more. It's just going to change the amplitude. It's not going to slow down and suddenly eventually dies out. That's because your force, your weight force has been there. It hasn't changed, right? When you started, the weight is pointing downward. It's the same throughout the entire process. It's not going to dampen the system. We need to use something else to achieve that. Questions so far? Yep. Correct. So the idea is that if we look at the equation, and this is your this is your holy grail. This equation expresses the displacement at any given time for your system. So the idea is that your x naught, or you can also look at the way the omega n is defined, which is square root k divided by m. Changing the initial displacement only going to change your amplitude. Quite often, if you don't have a damper, your initial displacement is your amplitude, unless they're trying to be annoying, like assignment 9 question 2, where you have a new datum, but then they're asking with respect to the old one, then you have to kind of insert something in there. It's a pretty overkill problem, that one. Questions so far? So a bit of a fun fact about these animation. The pendulum one that I showed, basically all these are made with somewhat ChatGPT fed in Python. The pendulum one took me 10 minutes. These mass springs one took me 50 minutes. You'll be surprised how dumb ChatGPT gets when I just want a single solid line at the bottom. It gives me back the code, and then suddenly the box is like out of frame. I'm like, what are you doing? But they do show you some pretty cool animations. I have some of them on Kirkus under supplementary material, especially for the effect of dampers. So right, again, your holy grail equation, x is equal to a cosine omega nt plus b sine omega nt. The bracket goes like this. Your a is just initial displacement, and then your b is initial velocity divided by omega n. If you don't have a starting velocity, the second term gets canceled out because it becomes 0, right? You have 0 velocity. So another thing, our natural frequency is calculated as radian per second. I don't know what's 3 radian per second. If you tell me it's 1 hertz per second or 1 hertz, that makes a lot more sense. So quite often they ask you to report it in terms of hertz. Have the equation to convert from hertz to radian and back from radian to hertz on your crib sheet. Same thing with RPM to radian per second. One of the questions last year had an RPM right from the start. I think a quarter to 1/5 to 1/4 of the student just couldn't, just because they didn't have the equation from RPM to radian per second. And then one of the students, because they messed up the conversion, they got something 1 times 10 to the 6 meter per second square for normal acceleration. Very impressive value. But I had a script, so I ran it. That student did everything else right. Just that conversion issue. So I think they lost like 2-3 marks, but everything else. But then, that's just how I grade. Somebody else might see it differently. Questions so far? Okay, so you might be wondering, a holy grail equation, why cosine and sine seems kind of arbitrary, kind of random. So the reason is that if you track the displacement of a block and you plot it with respect to time, it kind of looks like that. Again, you just have a spring, so you're just going to bounce back and forth. And if you rotate the wave 90 degrees, in this case, we get a perfect cosine wave. If you have an initial velocity instead, then it will become a sine wave. But this is why it's like sine and cosine. Questions? So you can tell, finally, here there's a solid line. I actually had to go in and manually code it. Bless you. Okay, viscous damper. So quite often we don't like the system just vibrating on its own. So we put something called a viscous damper, or like a, do you have other names for it? forgot. Just call it viscous dampers. So the way they work, usually they have some fluids inside, quite viscous. The idea is that, so the FBD looks like it's open here, but technically it's almost enclosed. The idea is like, let's say if you push it in, as that moves inward, you're basically squeezing some of the fluids around it, and that's going to slow it down. Usually you have some pretty viscous material, so let's say instead of water, you can put honey in there. Then it'll basically have more of a dampening effect. Now, if your spring forces are like rebellious teenager that goes left when you tell them to go right, dampers are the opposite. They are the grumpy boomers. They do not like changes that happens very rapidly. And this is represented by our force from dampers. It's still negative, they're still rebellious. But the x dot means velocity, so it's a function of your velocity. The faster you're trying to change a system, the more upset the boomers get, and same thing with the dampers. The c is just your dampening coefficient, Newton's second per meter. So if you had, sorry, go ahead. Yep, so they're decoupled. There are two different things. So quite often, your spring force is pushing it out, but then you have a velocity, right? Then your damper is going to be basically pulling it back in. This is how they actually slows each other down. The next slide has an animation, but if they're always in the same direction, it's going to make the problem worse. So they don't always flip direction, but quite often they do have like almost like a somewhat of a opposition, right? So imagine it's like, the teenagers versus the boomer. The boomer always wins. They wake up too early. Questions so far? So if you downloaded the slides before this, then the negative sign is missing. You might want to add back in. If you plug it into our new, or basically update our equation of motion, it becomes mx dot plus c x dot plus kx equals 0. This is assuming you have one spring and one damper. Questions on this? Okay, so let's see how it actually looks. So the green line is still a spring. The brown line is a damper. Theta is basically like how you determine if it's over, under, or critically down. On the left, there's a brown line there, but the actuator is off. So the way it works is just it goes back and forth. It's a little bit slower, but the amplitude stays the same. It's not going to change. Now, what happens when you have an underdamper, right, at the top right? So when you have an underdamper, that means you have an actuator, but it's kind of weak, right? It's kind of slowing it down eventually, but the spring is still kind of doing its thing. But eventually, the damper wins out, and then the system basically restores to equilibrium. Critically damped is very, very tricky to do. It's very sensitive, but it's the most ideal case where, so it accelerates it a little bit, and then it slows it down, so you don't overshoot. It's a kind of like a comfortable merging. Overdamp is what happens when you have a damper that is too strong. So the spring is trying to accelerate it, but the damper is like, nope, you're going at like 1 millimeter per second. That's basically how the overdamp looks, where it goes very, very, very slow. And you can also look at how the sign for this one, for example, you can see the directions actually quite often are opposite, with flips, negative versus positive. Questions? Yep.
Just one thing to add. Critical damp is the case where the motion will be dampened out the fastest way.
Yeah.
The question asks you what's the condition that the motion will dampen out in the shortest time, then it means that you will need to find this critical damp coefficient to be 1.
Yeah, critically damp is the best, but it's very, very picky. So with our new equation, we have a whole new kind of worm. Again, we don't like anything in front of x dot dot, so we update our standard form to this. This is kind of where theta is. pretty blocky mess. The idea is that depending on theta, you're going to have either critically damped, under damped, or over damped. So critically damped, your damper frequency has to be at the exact frequency of basically your system, or CC. If you're off by a little bit, it's not going to work. This apply on paper, it's great, but in life, quite hard to do. There's also lambda 1 and 2. Our examples don't touch on. We have dampers, so we don't go into critical under dam or over dam, right?
No.
Yeah, so we're not going to dive too deep into those. Questions so far? One thing I will say, when you have a damper, your x is no longer, a cosine omega n t plus b sine omega n t, because basically your motion decays, so you have a new fancy equation. Finally, rigid body. This is usually where they end up testing, and they don't have to make it fancy. So the sum of moment at O equals IO alpha. It's very, very important that you take the moment at O, the axis of rotation. If you're lucky, probably won't happen in exam, your O overlaps with your G. Of them is not, then you cannot take your moment at the gravitational center. You have to take it at the axis of rotation, and accordingly, your IO also has to be basically applied with parallel axis theorem. And again, we're OCD about this chapter, so instead of alpha, we have beta dot dot. Basically means the same thing, but kind of cleans it up. Now, if you only have a spring, you get negative k theta. This k is not the same as directly plugging your spring stiffness. Again, because you're taking a moment. So you have to consider that. Quite often that k has a pretty ugly multi-block items to it, as you'll see later on. Yeah, but once you find that, that allows you to find your omega n. Same thing with our basically linear system. Yep. You have to find it. We'll show you how you find today. I will say the example 1 and 2 was probably not the nicest to start with. But yeah, no, if they give it, it'll be too easy if they give it to you. Because then you just plug in omega n and then everyone's 90%.
So if you have a system that contains springs and mass, meaning the system has elastic property, which is due to spring, and inertial property, which is due to mass. The natural frequency is the square root of elastic property over inertial property. So you need to find the equation of motion, and using that, define the method. What's the inertial property of your system, and what's the elastic property of the system?
Questions? Yep.
Are there such things as static?
Interesting question.
What
Static force in rigid body.
An equal moment, or I guess in this case, be an equal moment on all times in the oscillation, and so they don't actually change anything in the method, and just make it harder to remove.
If your system is symmetric and your gravitational center is overlapping with your axis of rotation, then your gravity, your weight doesn't actually contribute, then it's a static. But be very, very careful. So last year, this was the final exam vibration problem. I think there's spring here. So you might be saying, well, the weight is here, so it's not going to do anything, right? But these are 3 different bars that welded together. So you have weight 1, weight 2, and also the weight 3. The weight 3, when you tilt it, then it's going to actually contribute. In fact, all of them do, because I think the axis of rotation is here. So yeah, weight 1 and 3 contributes to it. I think last year's finals question 5 is a pretty good example. It's not hard, but you have to know what you're doing in chapter 8 to get those marks. But yeah, that usually is what gets you above the average. So there's a 5-steps guide. This is specifically for rigid body, but you can still apply it to linear problems. You can always go gun-ho in, but I didn't take time to come up with this because I was bored and had nothing better to do. This gives you a frame, basically so you wouldn't get stuck. Just like any other kinetics problem, FBD, this is not the time to skim on the FBD. Draw it with a ruler, it clean. If you need to draw a second one to show omega alpha, do it. Second, we either apply Newton's second law or we take moment at their axis of rotation. Now, third one is our trigonometry simplification. This is exclusive to rigid body. Hide these from your calc or even any math prof. They will come chasing us. We are doing something very gross. Sine theta equals theta, cosine theta equals 1. The idea is that if you assume you're only messing with it by a tiniest degree, then it basically comes out fine. Do not use this on any other chapters or other courses unless you can, or basically they tell you to. This is only chapter 8. You put this in projectile, it's going to go full bar. Then finally, our standard form. Again, we don't want anything in front of our theta dot dot or x dot dot. Now, step 5, find omega, but sometimes that might find you x at a certain time, or like a theta. Then in that case, you just plug it into your equation. Questions so far? Okay. One last thing. The crib sheet actually had a typo. Pretty funny. Even one of the solutions given to us had a typo or had a mistake this week. So the original one has a sine omega nt plus b cosine omega nt. They're flipped. The idea is that a is basically x naught, right? If you start at t0, your amplitude is going to be basically above. So it has to be a cosine wave. Yeah, I think a crib sheet was made a while back by like an old student. This is the only mistake there are. Technically, they hit the mistake because they never show A or B. Did you sign it? Yeah, it's a class signature thing. So basically, if you find everything useful so far, you can put your name down. It's completely optional though. Okay, questions before going to problem 1? Okay. Right. So. Okay, we have a disk. We have 2 springs. They're basically symmetric. Quite often in vibration, they define the positive displacement direction. In that case, don't fight with them too much. Right, it's positive, which is convenient. They're asking about the largest amplitude x naught, so it would roll without slipping. Favorite, rolling without slipping. So you have seen rolling plus slipping gets pretty bad. So again, a 5-steps guide, start with FBD. So we have the disk here. We're going to assume it's pushed around yay much by x. We got a gravitational center here. We have weight. We have normal reaction. We have friction. This is because basically the disk is going to try to roll back. So that's why your friction is pointed towards the right. And we also have our spring force. Now, you might say, well, we technically have two springs, right? Have I forgotten the second one? Yes and no. So they are basically the same spring. So when you push this to the right, this one gets elongated, that one's get compressed, or the one on the left gets compressed. So the one on the left is the one on the right compressed is gonna push out. The one on the left that's being elongated is gonna pull it out, same direction. They have the same spring stiffness. So you can actually group it together and just say Fs is equal to 2k divided by 2x. Again, your x, traditionally we use delta x, but here we like to clean everything up, so just x. Yep.
And the force of friction goes
To the right.
because it's trying to go back.
Exactly. So think of it this way: when you try to mess with a vibration system, it's just going to try to undo your changes. So if you push it to the right, it's going to try to get back to the left or approach the equilibrium state. So yeah, this is why your friction is towards the right. Questions so far? Yep. No, so the initial displacement is defined by the question. Quite often, usually they define it so they can streamline it, especially with rigid body. If they don't state it, then ask the invigilator. If they allow rigid body to swing both ways, then it's not great because they have double the amount of solutions they have to do. Questions? Yep. Yep. So you push the disc towards the right, it's going trying to move back to the left. But there's no slipping, so it has to roll back. And so basically our omega has to go that way, like to kind of slip it back, and then our friction is towards the right. Questions? Okay, step 2 is Newton's second law. So this question is, again, pretty greedy. You have to do both Newton's second law and take a moment because, there's rotation. So vertical direction, pretty easy. Our normal reaction is equals to weight. Do that again for the x direction. Now again, our x dot dot is basically the same as our ax, but we like using dot dot and just x. For the x direction, we have friction force minus spring force equals mx dot dot. And if you sub this back in, we get friction force minus kx is equal to mx dot dot, and we're going to call that equation 1. Technically, you want to throw everything to one side, but we're going to have to combine a bunch of equations later on, so there's no point doing additional operations just yet. Questions so far? Now we have to take the moment. Counterclockwise positive, clockwise positive. Again, very important, we're taking it at O. In this case, we got lucky that it overlaps with our gravitational center. Do not always assume that is the case. But because it overlaps with our gravitational center, we can use IG instead of IO. Again, theta dot dot instead of alpha. So if we take moment at G, the only force that are giving us problem is our friction force times R. Our IG is half mr squared. Again, you should have this on your crib sheet for a circular disk. Forget if it's the last tutorial or 2 tutorials ago, there's a couple of tables, have all of them in crib sheet. Chances are they're not going to give it to you, because otherwise, why else would they let you have a crib sheet? And we're going to call that equation 2. Questions so far? Okay, we need one more equation. The question states no slip. That means our AG is equal to R alpha. And if we quote unquote translate it to chapter A notations, x dot dot on the left, R theta dot dot on the right. And that becomes our equation 3. So you can see how chapter A combines everything you've learned so far. If there's any shaky ground at any of the chapters, it will become very obvious and cause issue in chapter 8. So depending on your point of view of preparation, chapter 8, the 20 max is either the easiest or the hardest to get. Easiest if you know everything, but otherwise it is pretty tricky. Questions on equation 1, 2, 3? Yep.
What is FSR?
FSR, so we're taking it clockwise as positive. Yep. Yeah, the main reason is that we kind of knew omega is going clockwise. Omega is basically your theta dot. It's best to go with basically the, like say the positive x, and then in this case you have to go with the direction of the motion. Questions? The next step is pure math. The idea is that you combine equation 1, 2, and 3. You can choose not to copy this down. This is just pure substitution. Basically, you sub equation 3 into equation 2. You give your new term or new equation. You sub into equation 1. And that's going to give you something that looks like we're almost ready to be used. Again, we like our standard form. Yeah, this should be cosine. That should be sine. We like our standard form, so divide everything by mass and combine it. We're going to get x dot dot plus 2k divided by 3mx equals 0. This is our omega n squared. Don't forget the square, it's not just omega n. Technically, that would be our step 4. Yeah, standard form. Questions? Again, just pure substitution. The next step kind of goes back to the realm of dynamics. So the goal is to find a maximum displacement. So this standard form equation is nice, but it doesn't tell us anything, at least about that. So we need to basically kind of translate it into our displacement equation. Now, A is equal to x naught, B is equal to initial velocity divided by omega n. We are going to assume that the system is released at rest. If it's released at rest, 0 initial velocity, then the second term cancels out. Our displacement equation thus become x is equal to x naught cosine omega n t. Again, have a habit of putting a bracket to cover both omega and t. Another tip I have, when you do have both terms, calculate them as like part 1 and then part 2 and then add them. Don't try to gun-hole it and type the whole thing into your calculator. The chance of missing a closed bracket is astronomically high, and you won't be able to see the issue. By calculating them separately also allows you to check them more efficiently when you basically have time at the end. Questions so far about x is equal? Yep.
I think if t equals to 0, it's a limit of x.
The largest amplitude to x naught though.
Yeah, you just define x naught, but when it comes released, it has initial velocity, but x. That's why the answer key uses the sine function. The sine 0 is 0.
Okay, I see.
Initially, at equilibrium, it has velocity, but both way will work.
Yeah, okay, yeah, that makes sense. I was wondering. So yeah, I guess there's two ways to do this. Either way will give you the same answer, but so rather than assuming initially at rest, you can also assume initial displacement is 0. Then that's going to give you x is equal to x dot o divided by omega n sine omega n t. The idea is that when you have x, you're going to dt it. So the x dot is going to be omega n x naught sine omega n t. And then if you differentiate it with respect to time again, that gives you acceleration.
Still x equal to x naught sine omega, but with t equal to 0, sine equal to 0.
Oh, so x is omega n.
So it's just x naught.
Like that?
So this x will be just x naught sine omega t, because when t
Can I write it down?
Yeah, I can write it down. So x equal to x sine x naught sine omega n t. So x double dot equal to omega squared x naught negative.
But then
sine-
that's b though, right?
which one?
No, that's why I'm saying the solution is wrong, because
The
this,
solution is correct. This when t equal to 0, sine equal to 0.
yeah, but that means you're putting x into a, but then that's supposed to be followed
No,
by
no,
cosine.
here.
Yeah, but that's x dot divided by omega n. So
Why?
what happened to the omega n is is the definition by the textbook.
I don't get it. So it's just that x equal to this. So
No, it's not. This is the general form,
Yeah, yeah,
and
yeah.
I actually checked Wiley Plus in
Yeah.
front of my other class.
So your b will be x naught. A will be 0. Because
Then you're flipping the definition, though.
how? You
So if
assume you release.
no, so if you have an initial displacement
Yeah.
and at time 0,
I don't have it. It's at 0. It's at equilibrium position.
no, but if you use that equation, then that wouldn't work if you have an initial displacement,
It will.
because then it's gonna be a sine wave.
Yeah.
So at t equals 0, but
Yeah.
if you have an x not equals to 0, it's still going to be a sine wave. This is why I don't think the solution key was correct. Because then you start with 0.
You just shift it a little bit.
No, but the equation is wrong. It's from the textbook. I'm telling you.
Yeah, no problem.
It comes out the same because it cancels out in the end, but I don't think the solution is right. All right, welcome back. So both ways will give you the same answer, but I am convinced this on the left is the correct way. I checked textbook in front of my other class just to make sure A is followed by cosine, B is followed by sine. The idea is that if you start at time 0, if you have an initial displacement, it's going to be a cosine wave. If you fit it into a sine wave at t0 with an initial displacement, it's always going to start at 0, which doesn't make sense. But if you finish differentiating it again, you get this term, and we're trying to find the maximum displacement or acceleration. And to go from here to maximum, you basically just make your cosine omega n t into -1. That gives you omega n squared x naught. So I can actually show you the solution that's typed out given to us. So they use basically, this is what doesn't make sense, right? Because then your x is equal to x naught sine omega n t. That means no matter how much of an initial displacement you have, your system starts at equilibrium. It's kind of like, glitching through a wall. But it works out in the end because that sine omega n t becomes -1 anyway. But that's just my take. Questions so far? I'll say just focus on basically, omega x max dot dot equals omega n squared x naught. And since we know x dot dot is equal to our acceleration at the gravitational center, our x dot dot max becomes r theta dot dot max. Again, Ag is equal to r alpha. That's going to give us theta dot dot max is equal to omega n squared x naught divided by r. Questions? Yep.
So is it going to be the same if we say the maximum E is cosine is probably 1?
So if I turn that into +1?
Yeah.
But then it becomes a minimum, right? Because then the output, so it's maximum for here, but it's not maximum for x dot dot. Yeah, it becomes the minimum. And it will work, but then not for the next step. The next step is based on equation 2, where we are trying to find the maximum of FFR, which is why we got rid of basically our negative sign. So if we took minimum, then that would be fine, because it'll cancel out. But in this case, we're assuming everything maximum. And our friction becomes mu Sn times r on the right. We have half m omega n squared x naught. Sorry, there's no r, it gets cancelled out. Rearranging finally give us x naught is equal to 3 mg mu s divided by k. In an exam, they'll probably give you some values. They don't like asking you to do pure derivation, substitution like that. But the idea is the steps is quite similar. It might not ask you to do both Newton's second law and take the moment. But again, chances are they'll throw moment in there. Yep. So our equation 2 from way back up, so it's here. I'll just copy it again here. So our equation 2 looks like negative FR equals 1/2 mr squared theta dot dot. If we get the maximum, then this becomes magnitude positive, and then this becomes positive. You sub this in here, cancels a bunch of stuff out. Looks like something is missing in R. No, it's fine. It gets sub in and then cancels out.
Is that mg, like 3 mg?
Yes, sorry. 3 mg mu s. Yeah, last year when I was teaching, for the first half, I actually wrote on the PowerPoint slide deck rather than OneNote. And doing a standing up, my handwriting looks like 4th of July in Canada Day had a kid. And I looked at one of the class afterwards, I looked at my note or the slide, I was like, how did a student keep track of that? So after that, I switched to OneNote, improves it slightly. So questions before we move on to question 2? Okay. I think question 2 is a little bit more realistic what you might run into. So the system looks kind of complicated, but it's actually not too bad. The x1 and x2 is already predefined. We get mass 1, mass 2, we get K1, K2. We also have our viscous dampers. Now, the question is nice. We're given radius of gyration. So step 1, again, our FBD. With these rigid bodies problem, they will either tell you to have a small clockwise or counterclockwise rotation at the start. If not, it's fine. The direction of displacement doesn't change usually the response of the system. So we are going to assume small theta in the clockwise direction. We have O here, we have A, we have B. Now I did say small, but we're going to exaggerate it for the FBD. In reality, you took looking at maybe 1 or 2 degrees. Now, each of the pin is connected to a rod, so we're just going to give a dummy force, FA and FB. The rod is connected to 2 mass, M1 and M2. Now, when you rotate it clockwise, you're basically pushing M1 to the right. So it's quite important to show your displacement, because this allows you to basically come up with whether the spring force is going to go left or right. Unlike some of the other chapters problem, if the spring force direction is wrong here, there's no fixing it. This has to be completely right. So K1, X1. Now, for B at the bottom, when you rotate clockwise, you're basically pushing B away. So M2 get dragged out. So the spring is going to try to pull it back in. questions on the FBD so far in regards to the spring forces? Yep.
Are you going to throw those forces on the bar, or are you separating it first and then you're going to put the reaction on the bar?
So they are technically a internal force. You're talking about FA, right?
Yeah.
Yeah, they're. So remember how I think a couple weeks ago you have like the truck and then you have like a wheel on the back. The normal reaction when you do the flywheel is to the right, but when we include it into the truck, it turns to the left. So they act as an internal force of the system. They're in opposite direction, same magnitude. So they gets canceled out, but in this case, it's a dummy force that allows us to connect basically M1, the rod, and M2.
And why is it critical on the direction? Should it be like opposite K1 X1?
So if you look at FA, they kind of cancel out. It's like a bridging. It's a dummy force to connect two parts. Because then they're in opposite direction.
The direction doesn't matter.
Yeah. In fact, yeah, there could be an opposite direction. It would cancel itself out. Yeah, because K1, X1 is the important one. Now, the hardest part is the damper force. So when you rotate your system clockwise, you're moving it to the right. That's your XA. And that means you have a velocity towards the right because it's kind of moving that way. And because of that, you can deduce that our F damper at A is going to be to the left. Again, they are grumpy boomers. They find your changes. You find the velocity, they're going to go the opposite way. Now, same thing at B. It's basically going towards your right. So the damper force is going to be to the right. So, sorry, XB is to the left, so the damper force is to your right. Questions so far? Now, our A and B, the question wants us to determine everything in terms of X1. So we kind of have to basically go from A, B, and M2 to basically with respect to 1. So the way the system is set up, our A, VA, is actually the same as our X1. So XA is equal to X1. So X dot A is equal to VA, V1. Or basically X dot 1. The acceleration at A is also equals to acceleration at 1, or X dot dot 1. And the same thing for, B, where it's equals to X2, etc. Again, they're connected on the same rod. It might look like it'll change the system. If you have a very violent vibration, the pin is going to rotate, but again, we're cheating with our trigonometry simplification, where we're saying it's so small that we don't care. We're just going to force it into basically a cylinder. Questions so far? Right. Step 2, Newton's second law and moment. So again, start with Newton's second law. We're going to do Fx. Again, always a good habit to show the direction of positive when you do Newton's second law. If not for yourself, it also helps the grader. Now we're going to do it for M1 first. So we have basically our FA towards the left, negative MA. Our spring force is also towards the left, so minus K1 X1 equals M1 X dot dot 1. rearranging it, give us xa is equal to negative k1 x1 minus m1 x dot dot 1. Normally, you want to have x dot dot 1 from the front in a standard form, but if we do it now, we're kind of jumping the gun. This is why it's in step 4. It's not going to change the solution, but you have to come back to it anyway, so might as well keep it like that. Questions on equation 1? Okay, now we do the same for M2. Now I have kind of flipped the sign here. Normally you wouldn't want to do it, especially for x dot dot 1 because they're asking for it, but they don't care about x2. So even if you flip the sign here to showcase, it's not going to cause any issues. Because again, you just Newton's second law. You just have to make sure the forces and the acceleration are properly directed. That gives us FB is equal to K2x2 plus M2 x dot dot 2. Got equation 2. Even if you use left as positive, it will give you the same equation 2 in this case. But it shows you here that if you flip the sign, it's fine, as long as it's not the sign they're asking for. Questions on equation 1 and 2? Okay, feels like Thanos collecting the Infinity Gauntlet gems. Now we're going to do the moment. At O equals I naught theta dot dot. For once the question is nice, we don't have to calculate the mass moment of inertia. But it gets hectic when we take the moment. So we're just going to quickly sketch it out again. Get A and B here. You basically get your FA, FB, your FCA, and oops, towards the right, FCB. Again, you can replace it with spring force here, but then that means you have to update your FPD. That's going to give us FA times A minus FCA times A minus FB times B minus FCB times B equals M3 K naught squared theta dot dot. Now technically, when you take the moment, you want to use a perpendicular or perpendicular displacement, right? So you're trying to use this one, H1 instead. But our favorite trigonometry simplification, where cosine theta is equal to 1 and sine theta equals theta. That allows us to basically make some simplification. Technically, this is A, that's XA, that's XB. Sorry, that should be, oops. That should be B. But if you do cosine theta for the small triangle, I'm going to call that H1. Basically giving us H1 equals A, because cosine theta equals 1. It's the beauty of a vibration problem. You can cut quite a bit of corner. Questions so far? Now our equation looks pretty ugly if you plug everything in, because if you look at FA, it's K1x1, that's fine, but FB, K2x2, M2x2 dot dot, the equation wants it in terms of x1 primarily, so we have to get rid of x2 and x dot dot 2. And we also have to basically present the damper forces. To do that, based on a triangle on the right, we have xb equals xa divided by b divided by a. Translate it means x2 equals x1b divided by a. d dt, x dot 2 equals x dot 1b divided by a. If you do it again, x dot dot 2 equals x dot 1b divided by a. Sorry, x dot dot. Now, the acceleration at point A is equal to Ra alpha. So this comes from chapter 5. Again, this is why chapter 8 is such a boss. You really need to know everything to solve it. Subbing it in give us x dot dot 1. Wait, sorry. No, not subbing it. Writing it gives us x dot dot 1 equals a divided by cosine theta, theta dot dot. Simplifying it gives us theta dot dot equals x dot dot 1 divided by a. A lot of kind of broken trigonometry simplification here. But for the context of chapter 8, it works. Questions so far? There's only one step left. And the final answer looks extremely ugly. We sub literally everything into equation 3. Literally everything. If I write out the steps, it's going to be 5 o'clock, so I'm just going to plug the answer straight in. Oh yeah, not quite done yet. This is our answer. Yeah, the reason is so they have basically 2 mass, so 2 springs, and then also 2 dampers. They're also not symmetric, so you couldn't cut corners and just say like they double. Yeah, I hate to say it, could be fair game. This is a little overkill for exam. Questions? Okay, I'll leave it on for 20 seconds and then we'll jump into the other 2. We're running a bit tight, so we'll probably skip the water break today.